Okay, let's unpack this. Welcome back to the deep dive. We take your sources, find the nuggets of knowledge, and today, while we're continuing our OEIS series for number theory students like you, we're diving into a really interesting one. A000269?
Yes, A000269.
Our mission here is to get a handle on the sequence described as the number of trees with n nodes, 3 of which are labeled.
Okay.
So you're trying to count these tree structures, these arrangements, but with a twist, right?
Yeah.
3 specific nodes are marked, they're distinct.
Exactly.
And that's the challenge behind A000269. Sequence starts, let's see, 3 for N3, then 16 for N04, and it grows really fast. We're talking trillions pretty quickly.
What's really fascinating, I think, is the precision needed here. We're not just counting any trees. We're focused on these graph structures. But with that added constraint, 3 distinct identifiable nodes.
Right.
And that introduces a combinatorial challenge that's, well, quite different from counting unlabeled trees. It's a classic enumeration problem, actually.
On the n means the total number of nodes.
Yes, the total nodes. And it starts from N3, which makes sense because, you need at least 3 nodes to have 3 labeled ones.
Okay, that makes sense.
Yeah.
Now, something that jumped out at me in the OEIS entry were the key words, easy and nice. But when you see a sequence growing like that and you anticipate complex formulas, easy isn't the first word that comes to mind. What's that telling us? What's the secret there?
That's a great question. And it hints at something important. Often, easy in combinatorics suggests there's an elegant, maybe even a beautiful mathematical structure underneath. It means the enumeration, despite the large numbers, might be surprisingly tractable.
Okay.
It suggests maybe a clean formula or a straightforward derivation, even if the result is complex. So the question becomes, what is that structure?
Right.
And the formulas provided in the entry are a big clue.
Okay, let's definitely talk formulas then, because that seems key. There's this generating function, ax bx cubed times 3 minus 2 times bx, all divided by 1 minus bx cubed.
Hey.
For listeners maybe newer to this, a generating function is like a mathematical packing tool, a single expression holding all the sequence terms.
That's a good way to put it. A power series where the coefficients are the terms of your sequence.
But this ax depends on bx, which is the generating function for rooted trees. It's A00000081, another sequence. Why rooted trees? Why is that the key link?
That connection to A00000081, the rooted tree generating function, is absolutely central. See, a rooted tree isn't just any tree. It has a special node, the root. This gives it structure and orientation. And it turns out that counting rooted trees is often, well, simpler in many ways. Our sequence, A000269, for these 3 labeled trees, essentially builds on the solutions for those simpler rooted structures.
Okay.
It's really a powerful example of how you can break down complex combinatorial problems, even specific ones like this, into simpler, already understood parts.
And I also saw an alternative formula, AN equals A00000F24N minus 2 times A00000243. Does this just give the same numbers, or does that tell us something different about A000269, like its identity?
That's quite perceptive. Yes, it gives the same numbers, but it reveals a different relationship. While the generating function shows the construction from rooted trees, this kind of formula often hints at relationships through, say, inclusion-exclusion principles. Or maybe it's just a different way to count by combining or subtracting other known counts from the OEIS. It really highlights how interconnected these sequences are.
And speaking of connections, this sequence goes way back. It's in Riordan's 1958 book, Sloan's own handbooks from 73 and 95. Is its established place just because it's old, or is there something particular that makes it such a cornerstone example for students, especially given those formulas we just talked about?
It's definitely more than just age. The fact it appears in these foundational texts and that Neil Sloan himself authored the OEIS entry points to its significance. It's a classic problem, really. It helps illustrate fundamental principles of enumeration specifically, how you handle labeled elements, and how generating functions give you this powerful, compact way to solve counting problems.
So it's a good teaching example.
Exactly. It beautifully demonstrates the power of these mathematical tools.
Okay. So wrapping up our deep dive into A000669, we've seen it's the count of trees with n nodes where 3 specific ones are labeled. We've looked at its definition, the first terms, those elegant, if complex, formulas, and its deep roots in combinatorial history.
And the real beauty, I think, isn't just the numbers. It's how those formulas neatly connect this specific labeled tree problem back to fundamental ideas like rooted trees. It's just a great example of how combinatorial tools let us count and understand really complex structures by breaking them down. That kind of thinking is invaluable for any number theory student, really.
So for your own continued learning, maybe think about this. We talked about how labeling just 3 nodes changes the game significantly compared to unlabeled trees. What stands out to you about how such a seemingly small, precise constraint leads to such intricate yet elegant mathematical solutions? Something to mull over.